Metathesis reactions. There's some confusion about metathesis reactions and what they are. And also this morning, some people were asking about metathesis reactions. But unfortunately, not a whole lot of help. If you go to Wikipedia and you look for like metathesis reactions, you get salt metathesis reactions. Salt metathesis reactions are double replacement. AB plus CD yields. But the reason I don't call them double replacement is we don't always have the double replacement pattern. So for example, if I ask you, we might. If I ask you, what are the chemical properties of HCl? That's our AB. How many different CDs are you going to try? Well, maybe I'll go HCl plus NaCl, HCl plus KCl, HCl plus this. You're going to have an infinite number of CDs that you're going to try. It's going to be too much, right, to put it in that kind of pattern. And so the reason I call it metathesis is because when I think of metathesis, I think of the net ionic equation. In the net ionic equation, it's just the ions that like each other that react. All the other ions are what we call spectators. And so that's what we call favorable ion combinations, is the net ionic. So how do you get the net ionic without going through all the steps? All the steps are you got to write the complete equation and then the ionic equation and then the net ionic equation. Well, we're trying to develop this to where we gain enough experience and familiarity with these things in order so that we don't need to write out, If I have, let's say, HCl, I want to look at what metathesis reactions there are. I'm not going to list a whole bunch of CDs. What I'm going to do is I'm going to just take H plus. What anions does H plus like? Well, we already did that with nitric acid. And then I'll look at Cl minus. What cations does Cl minus like? And then that's my metathesis. So I'm not going to list a whole bunch of CDs. I'm just going to go through what ions we expect to get. And so, not everything has this double replacement pattern. But when I look at this, I look at the examples that they give here, these aren't very useful. These all fit the double replacement pattern or close to it. Sure, if I give you an AB plus CD, I could give you an AB plus CD like this. Here's my AB, HCl. Here's my CD, NaOH. Well, that's pretty easy, AB plus CD. But if I just give you this, I want a more general idea of what it reacts with. Of course, I know it reacts with NaOH, but what else does it react with? That kind of thing. All right, so in order to do metathesis then, we need to know things like solubility and electrolyte properties. So those are the types of things you need to review if you're a little fuzzy from Chem 1A, solubility and electrolyte properties, chapter 5. Well, let's just take a step back and look at metathesis in general. So metathesis, these are the favorable ion combinations that are the end result. In other words, the net ionic equation, favorable ion combinations. So how do we know when we get a favorable ion combination? The favorable ion combination forms something that's more stable. Usually something that's more stable is more strongly bonded. Usually things that are less stable are weakly bonded, more reactive. Things that are more stable are more strongly bonded, and less reactive. And so favorable ion combinations, then we look at, what types of things, do we see? And so now this link is working, I think. I just didn't publish it, I guess. And so we can go onto Canvas. It would be under files, or I don't know why I keep getting this pop-up. The pop-up blocker or something. Really annoying. And then I have the acid-base chart here on the right. So let's go ahead and, oops, save that. Let's see. Not a very big file. It's taking a long time to download. Is Canvas slow at downloading documents? Or is it pretty, you never noticed it? Okay. Maybe this computer was slow. Okay, in module, you need to have JavaScript. All right, sorry, this is going to take me. A bit of time here. I should probably post this handout also. I'm going to put this on. This is the complete version of the handout I gave you on acids. All right. So what are favorable ion combinations? So let's just take a look at HNO3 as an example here. And so I might ask myself, what anions does H plus like? Will H plus react with nitrate? And the answer is no, because HNO3 is a strong electrolyte. Strong electrolytes mean
they break apart and stay away from each other. The only time they'll come together is if you evaporate off all the water, and then HNO3 will come together. Otherwise, they're free ions in solution. This H plus like bisulfate, this is going the wrong direction here. In fact, these are all making stronger, but we know about the leveling effect, and we also know that these anions are so weak, they're not even considered basic. They don't have very much attraction for the H plus. Instead, what we want a stronger base than nitrate. If we want H plus to react with an anion, HNO3 is a strong acid. Strong acids are strong electrolytes. Strong electrolytes are 100% ionized. They're completely separated. However, weak acids aren't 100% ionized. Weak acids are partially ionized. And that partial ionization means this. So if H plus encounters this anion, what's going to happen? What's going to happen is H plus reacts with this. This is called trichloroacetate. So H plus reacts with trichloroacetate. What does it form? It forms trichloroacetic acid. Now, trichloroacetic acid is considered a weak acid. Actually, it's borderline strong, but it's still considered one of the strongest weak acids out there. And what we know about weak acids is they partially ionize. And that means that ion combination, the H plus and the trichloroacetate, is favorable because it's making a favorable link, a bond. And that bond is not so easy to break. This is what causes it to be partially ionized and not completely ionized. Whereas this bond is easy to break. And so this is completely ionized. Now, the weaker the acid, the less ionization there is. So this one has a fairly high degree of ionization. But if we go from, let's say, H plus and trichloroacetate, let's go to this. Let's take a look at this anion. Do you recognize this one here? It's CH3COO minus. Acetate. This is the second way of writing acetate. This is what we call the condensed structural formula for acetate. Now, acetate is a stronger base or a weaker base than trichloroacetate? Stronger. Remember, the stronger the acid, the weaker the conjugate base. So this is a stronger acid. Acetic acid is a weaker acid. Okay. Weaker acids, interestingly enough, are more stable. That is, the bond is more stable. The hydrogen likes to stay with the acetate. It doesn't like to break free like this. And so if H plus reacts with acetate, we form acetic acid, which is more stable, right, less reactive than HNO3. So we're going from a stronger acid to a weaker acid. Do you see that? Here. And so in metathesis, what are favorable ion combinations? Favorable ion combinations result, one, when we go from a stronger acid, it doesn't have to be a strong acid, just a stronger acid to a weaker acid. That would be a favorable ion combination. And so, other examples, so these aren't all ions, but good luck here. Other examples would be H plus, nitric acid, H plus with fluoride. Is that a favorable ion combination? Yeah, that's a favorable ion combination because HNO3 stay apart, but when H plus encounters a fluoride, it's going to bond to it to form HF. HF is a weak acid, and it's only partially ionized. Most of it exists as HF molecules. Does this follow the AB plus CD pattern? Yes and no. It would follow the AB plus CD pattern if I said HNO3 plus sodium trichloroacetate. And that would be my AB. The CD would be sodium. D would be trichloroacetate. And then we swap them. But we don't have to do that, do we? Because this could result from sodium trichloroacetate. It could result from potassium trichloroacetate, magnesium trichloroacetate. Any number of salts will give us trichloroacetate anion. Because all we need is a soluble salt, and that soluble salt breaks apart and frees up the anion. And that's what we need. And so rather than looking at it individually, like sodium versus potassium versus lithium, whatever, we'll just say, trichloroacetate, because the sodiums will be spectators, the potassiums will be spectators, lithium, magnesium, whatever, will all be spectators. And so we're jumping all the way to the net ionic equation, here. Okay, so that's stronger. And so let's see if there are other examples here for ions. Yeah, this could be a favorable ion combination here. Favorable ion combination would be ammonium plus hydroxide. If I take ammonium ions and mix it with hydroxide, what do I form? What I form is, if I take ammonium and mix it with hydroxide, I'm going to form water, that is the acid loses a proton, and ammonia. And so I'm going from a stronger acid, ammonium, which is very weak. Ammonium is at the weak end of the spectrum, but water is even weaker. And so here I'm going from a stronger acid to weaker acid. The weaker acid is more stable. Water is more stable than ammonium in terms of acid properties. Does that make sense? So this is it. Now, not everything occurs on the chart, and then there are some things I want to talk about here.
So I know for the homework we had to do the same thing for HCl, right?
Yes.
Just in the sense of how you did ammonium. And so like if you were to put this in like a to answer a question in terms of metathesis for ammonium, you would say that ammonium is reactive with anything lower than
Yeah, okay, this is tricky because metathesis deals with ions.
Okay.
But this ion also happens to be an acid. And so there are two ways to look at ammonium. One way is it's an acid. Forget it if it's an ion or not. Metathesis, I'm thinking ion, but acid base, ion or neutral, it doesn't matter. And it could be a cation or it could be an anion, it doesn't matter there either. And so if I were to use this in terms, the situation is with H+, that's both an ion and an acid. And so here we're talking about acid base. If you go back and look at what I did with nitric acid, and I did the, I broke it apart, and then I said H+ is just like the acid base that we just did. And so I didn't want to repeat it because I just repeat the exact same thing I said for acid base. Well, the same thing for ammonium. If I were to look at this in terms of metathesis first, I'd do it a little differently. When I use this chart, this is only for acid base. Metathesis doesn't have to be acid base. And in this case here, hydroxide is a base, but there are other anions out there like chloride, bromide, iodide, which we don't consider basic, or even anions out there that are somewhat acidic anions, like hydrogen sulfate. Hydrogen sulfate's an acidic anion. We don't really consider it base, even though it could act as a base. It's just too weak as a base. And so this would be it here, in this section, these are too weak to be basic and modern. And so my approach is a little different when I'm dealing with metathesis versus acid base. Now, ammonium is an acid, and so I would have knocked this out in looking at it as an acid. And ammonium as an acid, what bases does it react with?
The base is lower than ammonia.
Yeah, all these bases here, it'll react with. Now, those bases may not be ions. So for example, if I look at H2S, what bases does H2S react with? All bases stronger than HS minus. But when you look at NH3, it's not an ion. So NH3 we don't really consider metathesis in the sense that ion combinations. This is just acid base. And there are a lot of bases here that aren't ions. Are there? Actually, there aren't. Ammonia. But in reality, there are a lot of bases on here that aren't ions, too. And so, again, metathesis is just focusing on the ions themselves. So here, for ammonium, I would have done it like this. I would have listed ammonium's acid-base properties here. And then when I go to metathesis, I say see this, because a lot of the bases are ions, in addition to others. And what are the others? I'll talk about the others right now. Actually, before I do that, let me talk about this here. Trichloroacetic acid is a borderline strong acid. you know, and then we have acetic acid here. Acetic acid is a weak acid, pretty weak. And so what makes trichloroacetic acid so much stronger than acetic acid? And so here we try to analyze this based on structure and properties. And so the nice thing about writing formulas like this is a condensed structure formula. When we look at acetic acid, there are two ways of writing acetic acid, HC2H3O2 or CH3COOH. So this looks like triple O, this should be a COOH. And so the condensed structural formulas, we can generate the Lewis structures a little easier from those. So if I look at trichloroacetic acid, I'm going to have 3 chlorines on this carbon here. And then I'm going to have a COOH group. Now, COOH group, you think that might be a peroxide bond. A peroxide bond would be an oxygen-oxygen bond. The peroxide bonds are very unstable. And so it turns out the COOH group looks like this. This is called a carboxyl group, or carboxylate. If we get rid of that hydrogen and have the lone pair, the bonding pair converted into the lone pair, then that would form a carboxylate, which would have a -1 charge, versus the carboxyl group, which is this. If I look at acetic acid, the structure is very similar. Have a C that instead of having 3 chlorines bonded to it, I'll have 3 hydrogens bonded, and then I'll have my carboxyl group. The COOH group. The 2 oxygens aren't bonded to one another. If you tried to generate a Lewis structure with the 2 oxygens bonded to one another, you're going to have a lot of trouble with the octet rule, and you're going to have a lot of trouble with the formal charges. And these 2 structures here, the octet rule is good, and the formal charge is all at 0, which is good as well. So tell me why this one is a much better acid than this one. Well, more carbon-hydrogen bonds? Yeah. The hydrogen bonding, normally when we think of hydrogen bonding, there are 2 types of hydrogen bonding we think of. And hydrogen bonding is an intermolecular force, and covalent bonds would be an intramolecular force. There's an intramolecular hydrogen bond here. You know, when we have hydrogen bonded to oxygen, this would be an intramolecular hydrogen bond here. That is, this hydrogen is going to be attracted to that oxygen there. Yeah. And then there's intermolecular hydrogen bonding, because another acetic acid molecule will come and orient itself like this. Another acetic acid molecule might have the H over here and then the O over here. And so 2 acetic acid molecules can attract each other by hydrogen bonding, and this hydrogen here can be attracted to that oxygen by intramolecular hydrogen bonding. Normally what happens here is this, you know, we have free rotation about single bonds. You know, double bonds and triple bonds don't freely rotate. You can't twist them, but single bonds are easy to twist. And so this is like a propeller, this OH. This OH is spinning like this. But as the H gets close to proximity here, it slows down because there's an attraction there. Sometimes this attraction is so strong it stops the H there from spinning. You know? But anyway, these bonds here, this would be a polar covalent bond between oxygen and hydrogen. These would be considered non-polar covalent bonds because these bonds, the electronegativity difference is small. Carbon is a 2.5. Hydrogen is a 2.1. The delta EM, the difference in electronegativity, is only 0.4. So the 0.4 delta EM, we typically call that a non-polar covalent bond. But the hydrogen bonding is usually not used as an argument for the strength of acids, except for one. Do you know which acid in Chem 1A that hydrogen bonding was an important factor in making the acid pretty weak, weaker than expected? HF. HCl, HBr, HI are all strong. Why is HF weak? HCl, actually, I should write it in order. HI is strongest, HBr, HF. The difference in strength is not so significant, but a little bit. HF is 1,000,000 times weaker than HCl. Why is HF 1,000,000 times weaker than HCl? Well, there we could have used hydrogen bonding type arguments. What happens with HF is, a strong acid, what happens with a strong acid? Strong acids ionize or hydrolyze completely. They're strong electrolytes. HF wants to ionize or hydrolyze completely because fluorine's highly electronegative. Fluorine's being highly electronegative. There's a big delta plus on this. In fact, hydrogen bonding is a result of unusually large delta pluses, due to it's almost a full positive charge. And anyway, we expect it to break free, but what happens is it doesn't completely break free. So we expect it to break free and form H plus and fluoride, right? But this hydrogen doesn't completely let go. And this is what we call an ion-ion attraction. This is not a bond here because it's kind of distant, but it just doesn't completely break free. Fluorine has a little bit of hold on the residual hold. If fluorine has a residual hold on the hydrogen ion here, it can't be free to react like HI. HI, the H plus is completely gone. And the H plus is completely free to react with whatever base. But this one's not because fluoride's holding on to it. So this is called an ion pair. And so it's kind of like a hydrogen bond in a way, I guess. Well, I guess it's not. But it's an argument that we can use intermolecular or interionic forces in this case to argue about acid strength or base strength. And for these two examples, it's a little different. I wouldn't bring up hydrogen bonding. I'd bring up something else, which we talked about yesterday. We talked about two acids. One acid was weaker, the other acid was stronger. Do you remember what those two acids were? Let me tell you, one of the acids was nitric acid. What was the other acid? Nitric. Nitric and nitrous acid. What made nitric acid stronger than nitrous acid? Polarity, and what caused the difference in polarity between nitric acid and nitrous acid? Well, oxidation state, we could look at oxidation state. That's one way of looking at it. There are two ways I gave you of looking at it. One was oxidation state, the other was started with an I, two words. I-N, in, INT, in the, Close, but we don't call it induction. We call it the inductive effect. The inductive effect. Inductive effect, that is the big one in Lewis structures, the inductive effect. Inductive effect is often used to argue one acid stronger than the other. And we could do the same here. Give me the quick rundown. What did the inductive effect involve? Yeah, of like electron withdrawing, a chain of electron withdrawing, or chain of polarity, if you want. What's good is repetition is always good, and I recommend this. I always recommend this is to review your notes daily, so that inductive effect is because it's easy to forget this stuff. So, if you're on an exam and you have to spend a few minutes trying to remember what was that again, versus if you see it every day. If you see something every day, then it's easy to remember. It's like if you drive by some advertisement, let's say McDonald's advertisement every day, then it's fresh in your memory. But if you never drive by that, then it's not. And so it's useful to do. But anyway, the inductive effect here is this. What's more electronegative, chlorine or carbon? Chlorine. Chlorine's highly electronegative, so it's going to suck the electron cloud. Remember we talked about sucking or polarizing the electron cloud, distorting the electron cloud towards chlorine. What's that going to do? That's going to make carbon poor, right? And carbon being poor, it's different. Well, actually, both of these, but this one's kind of poor compared to this. Let's compare this carbon here. Which way does the arrow point here? Which one's more electronegative, carbon or hydrogen? Carbon. Carbon is just slightly more. But the dipole, this is called a dipole here, is going to be very small. So I'll try to draw a very small dipole. In fact, we call it nonpolar, so this dipole should be negligible. And so there's going to be a tiny dipole pointed towards carbon, which I'll try to show with these tiny arrows. These are the big arrows, these are tiny arrows, and these arrows are pointing. Now look at these two carbons. This one is a lot more rich. There's a lot more electron cloud density surrounding it. Do you see that? Visualize. And so it's a lot more rich. Well, this is going to impact the rest of the structure, having the electron cloud being sucked that way. And not only this, look at this carbon. This carbon is going to have electron cloud density sucked towards the oxygen, which in turn is going to make this carbon poorer. If it makes the carbon poorer, it has a greater pull. And then we end up eventually sucking it away from the hydrogen. Hydrogen being the least electronegative element on this compound, and we generate a large delta plus, a large polarity on the hydrogen. Versus acetic acid, when we look at acetic acid, we only have this one terminal oxygen, and that one terminal oxygen is sucking some electron cloud away from that, which is going to set off this chain of polarization. And it's going to result in a delta plus on the hydrogen. But when we compare the two delta pluses, the delta plus on trichloroacetic acid should be much larger than the delta plus on acetic acid. Does that make sense? So let's say you're hydroxide. If you're hydroxide, which H would look more attractive to you? This H up here or this H down here? Well, the one that's more positive. If you're a hydroxide, you're negative and you're looking for positive, so this H is going to be much more attractive. How about these H's over here? These H's over here, the bond polarity is so small that, these are pretty much have negligible delta pluses on them. So if you're a hydroxide, you aren't really going to be attracted to these three. These would be called non-acidic hydrogens. And that makes acetic acid only a monoprotic acid with one acidic hydrogen out of 4. So we call this the inductive effect. That's one way of looking at it. This is what's described in Chem 1A. But to add to this, what we want to do is we also want to look at oxidation states can help us too. And when we look at the oxidation state, let's take a look at the oxidation state on this carbon here versus this carbon here. All the other atoms are the same. Usually you have the carboxyl group here, carboxyl group. It's just this group that's attached to the carboxyl group. So what's the oxidation state of this carbon here? Not zero. You know, remember oxidation state is winner take all. Winner take all electrons. The winner is the more electronegative element. So chlorine versus carbon. Who takes all the electrons? Chlorine or carbon? Chlorine takes all. So these two electrons go to chlorine. These two go to chlorine, these two go to chlorine. So carbon gets none of those. Carbon versus carbon. Well, carbon versus carbon's got to be a tie. Even though those two carbons are different, we're going to call that a tie. So carbon ends up with only one of these two electrons. The other of those two electrons goes to the other carbon. So carbon in the structure only ends up with one electron. But how many valence electrons does carbon contribute to those structures? 4. So it contributed 4, it ends up with 1. That means it's lost 3 electrons. It has a deficit of 3 electrons, which gives it a positive 3 oxidation state. Okay, let's look at this carbon here. What's the oxidation state of this carbon? It's not 0.
No, isn't all the electrons from hydrogen goes to?
Yes.
And then carbon has wait, -4?
So, okay, carbon versus hydrogen, carbon wins. That's 2, 4, 6. So it takes all 6 of those electrons. Carbon versus carbon, it's a tie. So carbon only takes 1 of those. So that's 6 plus 1 gives us 7 electrons. This carbon ends up with 7 electrons. How many valence electrons did carbon contribute to the structure? 4. It ends up with 7. It's got how many extra electrons? 3. So 3 extra electrons gives it a charge of -3. So compare these two carbons. One carbon is +3, the other carbon is -3. Which one is electron rich? Which one is electron poor? Yeah, this is electron.
Wait, 4. No?
This one's electron poor. It's missing 3 electrons. This one's electron rich. It has 3 extra electrons. So this one being electron poor is it's going to be like, you know, it's going to be like a desiccant. You know what desiccants are? Desiccants suck the water out of everything. Like if you put a whole bunch of desiccant in here, it would dry things up. You know, they call mummies, like those Egyptian mummies, desiccated because they had all the water sucked out of them, basically. And so if you're out in the desert, everything's desiccated. You know, it's dried up. And so this is going to suck the electron cloud density towards this, right? And make this more polar. This one, when we look at this carbon, however, is not electron poor. This carbon is electron rich. If it's rich, then it's going to contribute some of the electron density to the carboxyl group here. This one sucks the electron density out of the carboxyl group, making this one more acidic. This is the exact same carboxyl group, but we attach an electron-rich group to the carboxyl group. It's going to push electron density the other way, making the delta plus smaller. And so in terms of polarity, this is a much better acid than this. A better acid, well, the base, like even a weak base like water is a pretty weak base, but water can pluck off some of the hydrogens. And so in trichloroacetic acid, water can pluck off a much higher percentage of these acidic hydrogens than in acetic acid. Water would have a much harder time plucking hydrogens off of this. And so this makes it a stronger acid, trichloroacetic acid, and it's going to be more ionized in solution. That is, water is going to be able to pluck more of the hydrogens off than this. And so this makes this acid more stable, less reactive. This acid's less stable, more reactive. And so there's a little difference here between trichloroacetic acid and acetic acid here. We'll look at bases later. Bases, we analyze those a little differently. So as far as favorable ion combination, stronger acid, weaker acid, this is the same as acid base. And so that's just some overlap. And so this is why when I did HNO3, I didn't bother doing it again for metathesis. I just had to look at what we did for acid base, basically. And it's actually, acid base is more comprehensive because you could have neutral species in addition to ions, but essentially the same analysis. Okay, the other thing of favorable ion combinations are precipitates. You know, what makes a good precipitate? Well, what are precipitates in the first place? Precipitates are salt, insoluble salts. And insoluble salts, when we think about insoluble salts, like, give me an example, like silver chloride, we think of a salt or an ionic lattice. Do you guys remember ionic lattices? You know, like, there are some ionic lattices. Sodium chloride lattice, that's a very common one. I did lattice energy. But you remember seeing these types of things? This is the ionic lattice. And so if we have an insoluble salt, it's insoluble because the ions are strongly attracted to one another. The ions like each other. If we have a soluble salt, then the attractions are weaker. The ions don't like each other as much, and so they can be broken apart. And so precipitates have strong ion-ion interactions. Strong ion-ion interactions in the ionic lattice are strong ionic bonds. And so when we form a precipitate, that lattice is going to have stronger ionic bonds. So sodium chloride is soluble. And so what happens is water can tear apart this lattice easily, and we have 3 sodium ions and 3 chloride ions. And so the ion-ion attractions aren't as strong. So if you have salt water, you know, the salt is dissociated into sodium and chloride. But if you have salt water, you don't get a precipitate. The precipitate would indicate that the ions are attracted enough, they like each other enough to form a solid lattice. However, if you have like magnesium oxide, you know, magnesium oxide, that's a very strong lattice. Or magnesium carbonate or calcium carbonate. So if you have calcium carbonate, what's going to happen is calcium ions like carbonate ions, and the calcium and carbonate are going to come together to form ionic bonds and an ionic lattice. So let's take a look at the calcium carbonate lattice here. I don't want lattice energy, I just want the lattice. The lattice energy is going to indicate how strong that lattice is. So here, this is a much stronger lattice. Calcium and carbonate will precipitate out of solution. Those ions really like each other. And once the ions come together, calcium carbonate doesn't dissolve in water. So when you put sodium chloride in water, it dissolves. When you put calcium carbonate in water, it doesn't dissolve because the ions are strongly attracted to one another. And so we look at what makes a strong lattice. And so when we look at the patterns for strong lattices, typically what makes a strong lattice can be attributed to at least the first level to Coulomb's law. Did you cover Coulomb's law in Chem 1A? Coulomb's law just says the force of attraction between ions. You know, I want to look at how strongly the ions are attracted to one another depends on 2 things. The force of attraction between 2 ions depends on the charge on ion A and the charge on ion B. and something called d squared. D squared is the distance between the center of the ions. When you look at a lattice like this, what's the distance between the ions? The distance between the ions is 0. The ions are touching one another. When you look at any salt lattice, all the ions touch one another. So the distance is 0. This is not the same distance because, you know, if you put 0 in here, then you'd have infinite force. But what we aren't looking at the distance between the ions. We're looking at the distance between the center of the ions. So let's say we have a calcium touching a carbonate here. We're not looking at this distance because they're touching. So you get a calcium, this is really washed out, but in a carbonate here. Instead, what we're going to look at is we're going to look at the distance between the center of the calcium and the center of the carbonate. And what that's going to do is it's going to give us an indication of the size of the ion. The bigger the distance between the center of the charges, the bigger the ions are, you know, because they just take up more space. The smaller the distance, the smaller the ions. And so this allows us to treat certain ions differently. So for example, chloride. Let's say chloride is a -1, bromide is a -1. And so you might think, oh, chloride and bromide are going to behave the same. No, they aren't going to behave the same because chloride is, let's say, this big, bromide is this big. And so if you have a chloride, you have -1 more concentrated in a smaller volume. If you have bromide or iodide, the -1 charge is more diluted. In other words, it's spread out over a much larger volume. And so the higher the charge and the smaller the ion, the more reactive it is. That is because it has a higher, what we call charge density. So this is the same thing. If you have concentrated lemonade versus dilute lemonade, like a big ion would be like dilute lemonade. But if you have a small ion with the same charge, that would be like concentrated lemonade. Okay? And it's going to be more reactive as far as Coulomb's law goes. And so we can see, you know, just based on charge, sodium chloride is soluble. The ionic bonds are weaker. Calcium carbonate is insoluble. The ionic bonds are stronger. Why? Well, one thing is the charge. You know, if you look at the charge Za, it's 2 plus, Zb is 2 minus. So 2 times 2 is equal to 4. Well, 1 times 1 is equal to 1. So if they were the same size, calcium carbonate would be 4 times stronger, more strongly bonded, more strongly attracted to one another than a 1-1. Does that make sense? Well, that's without ignoring the distance, you know, the size. And we also look at the size. So what we see in terms of solubility is that the lower the charge and the bigger the species, the more soluble they are, and the less reactive they are in metathesis. The smaller the ion and the higher the charge, the more reactive they are in metathesis. Because we're looking at ion attractions, you know, positive, negative attractions for right now. But that's only one aspect of it, because there are other aspects to this, because not everything is just purely electrostatic like this, you know. There are other things where we got to look at the shapes of the orbitals and this kind of stuff. We have to look at more covalent interactions. And covalent interactions can't be simplified into something like this. It's a little bit more complicated. So what will give us an idea of a favorable ion combination are the solubility rules. If it's soluble, it's weak, weakly attracted. If it's insoluble, it's strongly attracted. If it's insoluble, it's going to precipitate. And so let's take a look at the solubility rules here next. I'll just write them over here. That is a precipitate. What we're looking for is a PPT. PPT is just an abbreviation for precipitate. Precipitates are favorable. Ion combinations. Okay, so looking at the solubility rules, let's break them down over here. So, what are the biggest elements on the periodic table? On the left or the right? The biggest atomic radii, let's say. Biggest atoms. On the left or the right? The left, yeah. The right, it gets smaller. So you start off on the left big, and then it starts to shrink. On the bottom or the top of the periodic table, what are bigger? On the bottom, yeah. And so, solubility rules are going to go like this. So the first one is, I break them into 7. And so the first one is group 1 and ammonium. Group 1, the alkali metals, big atoms. They're big atoms, but the ions are smaller, right? So if a sodium atom is this big, how big is a sodium ion? You know, roughly? If a sodium atom is this big, is a sodium ion like, what would you guess? Sodium atom is this big. Would a sodium ion be bigger or smaller? It's smaller. Would you guess it's like 3/4, half, quarter of the size? What would you say? Roughly. It's about half the size. And you know, you think, what about the others? Well, the others are about half the size too. And so that's a rule. It's not a law. You know, the little exceptions here and there to the rules. But you know, if sodium's this big, then sodium ion's about half the size of that. But still, it's big. And so the group 1 cations like sodium, potassium, lithium, whatever are big. This ammonium's big, low charge, +1. That means these aren't going to be really strongly attracted to anions because they're kind of, you know, this is kind of like the, what did I say, the dilute lemonade versus this is the dilute, you know, it's not that concentrated. And so these are soluble. So it doesn't matter the anion. I could have a very reactive anion, like phosphate. You know, you think about phosphate, what makes phosphate more reactive? Well, the size is kind of big, but what's the charge on phosphate? 3-. Phosphate's pretty reactive in metabolism, it's got 3-. But when you pair it with like sodium, it's not going to precipitate. Those will be spectators. And so if you have sodium phosphate, the sodium will be floating here, the phosphates will be floating there as spectators. We need something to precipitate out, do something, you know. They're not really doing anything. So no matter what anion you pair with these, it's not going to happen. So even if you have a highly charged anion, we don't see anything. And so we look at the cation first. Group 1 and ammonium cations are soluble. Then we look at the anions. The anions, we're going to start off with this. We're going to start off with nitrates, acetates. Acetate I'm going to write as a standard, C2H3O2- rather than the CH3COO-. And chlorates. Well, what do these have in common? These are kind of low charge, you know, low negative charge, they're kind of big. You know. So they aren't very reactive in metathesis. Even if you put these with a fairly reactive cation, like let's say iron 3. Iron 3 is a really small cation with a 3+ charge. You know, iron 3 you'd expect to be pretty reactive in metathesis. Even if you pair those up with iron 3, it doesn't precipitate. You know, and so if I have some nitrate in water and I dump in some iron 3, nothing's going to happen. The iron 3 is going to pass by, the nitrate's going to pass by, they aren't going to come together and precipitate out of solution. It's because, yeah, they don't have enough charge density to attract that iron 3. And so these are all soluble, all soluble. Then we're going to move on to chlorides, bromides, and iodides. Chlorides, bromides, and iodides are soluble as well. All soluble except, so here there's some exceptions, except when paired with silver ion. Do you know what the charge on silver ion is? +1. There's only one charge on silver, and it's +1. There are two charges on lead. Do you know what the two charges on lead are? Not +1. +2 and +4. Okay, so except for silver, lead-2, you'd expect lead-4 to be more reactive, but it doesn't occur on this list. And mercury. There are two charges for mercury. What are the charges on mercury? +1 and +2. Mercury +1 has two mercuries, each at +1, giving a total of 2+. And so chlorides, bromides, and iodides are all soluble except when paired with these. But you're thinking, you know, we have an iron 3. An iron 3 has a 3+ charge and is very small, versus silver ion. Silver ion's only got a 1+ charge. So why is silver ion precipitating out with, let's say, chloride, but iron 3 won't precipitate out with chloride? And so not everything is based purely on coulombic interactions. There's also some covalent interactions in there as well. And so that leads to this. A lot of these heavy metals, silver, lead, mercury, have a high degree of covalent bonding percentage in there. In fact, this is why lead-4, you'd think lead-4 would be precipitating out for sure. If I had lead-4, I should be able to precipitate out chloride because it's a much higher charge, right? Much better coulombic interaction. But the problem with lead-4 chloride, PbCl4, is it doesn't form a lattice. PbCl4 forms molecules because it's much more covalent than ionic. And since it forms molecules, those molecules can be polar and dissolve in water to a much greater extent than PbCl2, which forms a lattice. Same thing, mercury 2 chloride forms molecules. For molecules, the solubility rules are a little bit different. For molecules, the solubility rules go like this. Like dissolves like. Have you heard like dissolves like? Oil, does it like water? No, because oil is nonpolar, water is polar. They're unlike, so they don't dissolve one another. Whereas alcohol, you know, small alcohols like ethanol likes water. So we have chlorides, bromides, and iodides, and then after chlorides, bromides, and iodides, we look at sulfates. Now, sulfate is a much higher charge. It's 2-. But sulfate is also kind of big because it's got 4 oxygens around the sulfur. It's kind of a big ball. And so, on the one hand, you expect it to be more reactive. On the other, it's kind of big. So the negative charge is more diffused through the volume. But anyway, sulfates turn out to be mostly soluble, except for silver. Silver is borderline, so I'm going to write a little asterisk next to silver. Lead-2 and sulfate really like each other. That forms a highly insoluble salt. So if lead-2 encounters sulfate, we get a very nice white precipitate from that. Mercury 1. So mercury 1 sulfate, they like each other. Mercury 1 and sulfate ions. Mercury 2 and calcium, strontium, and barium. These like each other as well. Now there's some strange ones like magnesium. Why is it magnesium? Magnesium, is it bigger than calcium or smaller than calcium? Magnesium. Smaller. Magnesium's smaller, so why isn't it here? Magnesium sulfate turns out to be soluble, but we expect a stronger interaction there. And so there are other factors in addition that we have to consider. But, you know, at a simple little level, the Coulomb's law kind of works. Okay.
What is the element after calcium?
Barium. Calcium, strontium, and barium. All 2+. Well, but what if we had iron 3 sulfate? What would you expect for iron 3 sulfate? Iron 3 sulfate, I would have guessed, would be insoluble. You know, highly charged iron 3 plus highly charged sulfate, I'd expect it to form a precipitate. Those ions should like one another. But it doesn't precipitate, so that means the iron 3 goes by sulfate, nothing happens. It doesn't precipitate. Why? Well, we'd have to look at what's happening there at a structural level, which we aren't going to do. We're just trying to look for patterns right now in terms of reactivity. Okay, so these are all the mostly soluble species, or all soluble or mostly soluble. Then the other half of the chart deals with the mostly insoluble species. And the mostly insoluble, okay, or start off with like hydroxide. Hydroxides are mostly insoluble. Now it's only a -1. It's a -1. Why should it be in, well, oxygen? Oxygen is a pretty small atom. It's pretty far on the right side, so it's pretty small. And so if we have oxygen, you know, then we have that negative charge on oxygen. It gets a little bit bigger, but still it's pretty small. And so hydroxides are insoluble, except for group 1, ammonium, calcium, strontium, and barium. So what this means is if a sodium ion passes by a hydroxide ion, is anything going to happen? That is, are they going to come together and bond to form a precipitate? So if a sodium ion passes by a hydroxide ion, do they bond together and precipitate, or do they just keep going their own way? They don't precipitate. They just keep going their own way, which means it's not a favorable ion combination. It's an unfavorable ion combination, right? And so that's group 1, sodium, potassium, lithium. If ammonium passes by a hydroxide, will it precipitate? It won't precipitate. It won't precipitate, but this is metathesis. And so we have to keep things separate. Because we know that if an ammonium passes by a hydroxide, it won't precipitate, but it will do what? It will do an acid-base reaction. If ammonium passes by hydroxide, we're going to get a reaction. We're going to get a proton transfer reaction. So ammonium is going to react with hydroxide to form water and ammonia. So this is an acid-base reaction, but in terms of metathesis, nothing's going to happen here. That is, we aren't going to form a precipitate in that sense. Even though this is a favorable ion combination, the favorable ion combination is covered in the acid-base part, which was part 1 of this, or what we did originally over here. Uh-huh.
So all the metathesis reaction always form.
No. No, this is, let me repeat this differently. This is a favorable ion combination, ammonium and hydroxide, but this is also an acid-base reaction. And then we're looking at ion combination reactions which precipitate. And so when we did metathesis, the first one we looked at were acid base, stronger acid to weaker acid. Okay, and so that would be classified under two categories. One, both metathesis and acid base. Okay. The precipitation would just be classified under metathesis in this case. There are precipitation reactions that aren't classified in metathesis at all, which we'll look at later. All right. If a calcium went by hydroxide, anything happen? Strontium? Barium? What about an iron 3? If an iron 3 went by a hydroxide, would something happen? Yes, you're going to get a precipitate, iron 3 hydroxide. If a lead 2 ion went by hydroxide, will something happen? Yes, you're going to get a precipitate. So by this way, we do like process of elimination or whatever, we can figure out that, okay, what likes hydroxide? Well, what likes hydroxide is every other cation except for these. And so list any cation. Well, how about magnesium 2+? Does magnesium 2+ like hydroxide? Yes, you're going to get a precipitate there. Magnesium hydroxide. And so in this sense, we can just make a very long list, chromium 3, yeah, chromium 3 hydroxide. Manganese 2, yes. Manganese 3, yes, And so in this way we can sort it out versus if we had to do something like this. If we had to do this by a double replacement, then we'd start off with one hydroxide, sodium hydroxide, and then try to add a whole bunch of CDs, which would be too much. Okay. So I want to talk a little bit about strong bases. We know that hydroxide is a strong base. Hydroxide is the strongest base that exists in water. Does that mean all hydroxides are strong bases? So let me give you an example of two hydroxides. One hydroxide is sodium hydroxide. Do you know you can buy sodium hydroxide at the supermarket? Do you know what it's called at the supermarket? It is called, well, I was just at Ralph's a while back. I was looking for drain cleaner, and I saw this one, Red Devil Y. I wonder, yeah, this is it. Oh, actually, it wasn't in packaging like this. The packaging looked a lot different at Ralph's. This is, no wonder, this is called Red Hot Devil Y. At Ralph's it was Red Devil Y, which has much plainer packaging. Let's see. Oh, here it is. I wonder if the Red Hot Devil Y is better than the Red Devil Y. Anyway, it's a drain opener or drain cleaner. You know what it's made out of? Actually, Red Hot Devil Y says what it's made out of. Let's take a look at the Red Hot Devil Y says it's made out of. And the Red Devil Y is made out of the same stuff, so they're probably the same. Yeah. Sodium hydroxide. So you can buy sodium hydroxide at the supermarket. In fact, I was going to buy it, but I ended up buying Drano or something like that. I forgot what I ended up buying. Liquid Drano. There are other kinds in addition to Y in there. That's what I was thinking about. So we have sodium hydroxide. Sodium hydroxide is a strong base or weak base? Strong base. Another hydroxide you can buy at the supermarket is this one. Let's see if I still have it. Milk of magnesia. Have you heard of milk of magnesia? Milk of magnesia used to come in this pink bottle. Let me see if I can see the, or blue bottle. Blue bottle. Okay, this is milk of magnesia. Do you know what milk of magnesia is made out of? Magnesium hydroxide. So we can buy hydroxides at the supermarket. We can buy sodium hydroxide, which is drain cleaner, and milk of magnesia. What's milk of magnesia used for? Yeah, constipation, laxative. I have a question here. And the question is this. Let's say you needed some milk of magnesia. So you went to the medicine cabinet, but there was no more milk of magnesia. But you remember, I have another hydroxide. The other hydroxide is drain cleaner underneath the kitchen sink. So if you run out of milk of magnesia, which is magnesium hydroxide, can you substitute sodium hydroxide for magnesium hydroxide? No? Why not? Why not? The sodium, are you sure sodium hydroxide? This has, magnesium hydroxide has 2 hydroxides for every magnesium. Now, if I think about magnesium hydroxide, it's MgOH2. 2 hydroxides. Sodium hydroxide only has 1 hydroxide. So isn't magnesium hydroxide a stronger base with 2 hydroxides versus sodium hydroxide and 1 hydroxide? Somebody might argue with you saying that there's more hydroxide in magnesium than there is in sodium. Magnesium should be a stronger base. So I should be able to drink the drain cleaner because it has less hydroxide. Is that a good argument? No, not at all. You're absolutely right, but I want you to tell me why magnesium hydroxide is a weaker base. It's not because of the inductive effect. Uh-huh.
Is it because
Yes, it's because of the charges, right? If we think about this, the big difference here is this. Magnesium is 2+, sodium is plus. Sodium hydroxide is soluble in water. Magnesium hydroxide is insoluble. If magnesium hydroxide is insoluble, what that means is the hydroxide is locked in the lattice. It's not as reactive. You know, if you look at the drain cleaner is also solid. This is what the drain cleaner looks like. This is solid sodium hydroxide. If you take that solid sodium hydroxide, it dissolves in water. If this were solid magnesium hydroxide, it doesn't dissolve. Have you ever had milk of magnesia? I think I had it as a kid. I hated it because what does it taste like? It tastes like a paste, you know, just a dry, desiccated powder paste in some suspension in water. So when you drink it, it tastes like chalk, you know, like you're eating chalk that you write on chalkboards with. That's what it tastes like. Doesn't taste so great, but that's good because magnesium hydroxide is not soluble. It keeps the hydroxide in the lattice. The hydroxide can still react as a base, but it has to be attacked on the surface of the solid here. Whereas in sodium hydroxide is totally free. And so what we say for hydroxides, all hydroxides are strong bases, but not all hydroxides. Instead, what we should say is this. We should say that the soluble hydroxides are strong bases. The insoluble hydroxides are weak bases. What are the soluble hydroxides? These are the soluble hydroxides. So sodium, lithium, potassium, cesium, rubidium, all those are soluble hydroxides. Those are strong bases. Ammonium hydroxide, strong base. Calcium hydroxide, strontium hydroxide, and barium hydroxide are the strong bases. Every other hydroxide is a weak base. NaOH is soluble in what? Yes. So if it's soluble, what happens? Well, the sodiums break free from the hydroxides. And the hydroxides are free to attack acids. Whereas magnesium hydroxide, the magnesium and hydroxides don't break apart. So the hydroxides are kind of stuck. They want to react with acids, but they can't because they got to break free of the lattice first to react. Does that make sense? Or the acid has to attack the surface of the crystal. I'm sorry, can you repeat that? It's hard to hear sometimes. This thing has this weird switch. What was that? Why sodium hydroxide is soluble?
Yeah.
Sodium hydroxide is soluble because sodium +1, hydroxide -1, it doesn't form a strong enough lattice. So it has to do with the size. So sodium is kind of big. Hydroxide is pretty small though. And so when we look at hydroxide, there's an OH minus here. It's kind of small. It has to do with the how big sodium is. Sodium versus something like magnesium. Magnesium is smaller than sodium, and not only is it smaller, it's +2. So when we have a hydroxide come over here, there's a much stronger electrical attraction here than there is here. This much stronger electrical attraction results in ionic bonds that are stronger. These ionic bonds are weaker. These ionic bonds are weak enough that water can break it apart. These ionic bonds here are too strong that water can't break it apart. So when you drink milk of magnesia, you aren't drinking an aqueous solution. You're drinking a paste, a solid paste. The solid paste they call a suspension. So when we look at milk of magnesia, we go back here. Let's see if we can see. If we go to WebMD here, you see milk of magnesia suspension. They can't even get they can get a tiny bit to dissolve, but most of the magnesium hydroxide is just solid. And they grind up the solid to make a very fine powder, and then they suspend this powder in the liquid so that you can drink it. It's like a very, very thick milkshake, you know. Let's say you had a lot of protein powder in there. This is what it's going to taste like, kind of thing. Or the texture is going to feel like that. Okay, yeah, you would not, if you ran out of milk of magnesia, you would not drink sodium hydroxide. That would kill you. It would kill you because all that free hydroxide ready to attack whatever it can attack, you know. But this is kind of slow release. It's okay. This always reminds me of this. This is something I usually show in Chem 1A, but since this is appropriate for what we're talking about now, let me just show it to you now. Yeah. We're going to be talking about complexes, and EDTA, ethylene diamine tetraacetato, is what we call a complexing agent. This is a big, gigantic anion. It's a 4- anion. And this anion loves to complex or eat metal cations. And so if we have an EDTA, the EDTA just encapsulates that. It's called a chelating agent. Chelating agents are like claws. And so it encapsulates metal. So EDTA, like this, is used as a drug or medicine for the treatment of lead poisoning. So if you have lots of lead ions in your blood, you can take EDTA, and the EDTA hopefully will encapsulate the lead so that the lead can't react with other things. Well, it turns out there are two medicines for lead poisoning. One is calcium EDTA. It's actually disodium calcium EDTA, but they aren't showing at all. Calcium is 2 plus, EDTA is 4 minus, so there's 2 sodiums missing. But when we compare the 2 drugs, the only difference is this one has a calcium, this one has all sodiums. So this would actually be tetrasodium EDTA, but they're just comparing the 2 here. So we have calcium EDTA versus sodium EDTA. Which one do you think is going to be more aggressive? The sodium EDTA drug or the calcium EDTA drug? Which one would be a more aggressive drug at capturing these lead ions that might be in your blood? The sodium? Why do you think the sodium would be?
I was thinking like the example you gave, like there's like
Yeah, right. Here, if we want hydroxide to react, then we don't want to hinder the hydroxide, right? We want the hydroxide free to react. So sodium hydroxide, the sodium breaks off from the hydroxide is free to react. Magnesium hydroxide, magnesium doesn't let go of the hydroxide. Magnesium wants to hold on to the hydroxide and doesn't want the hydroxide to react with anything else. Right? So magnesium hydroxide is like this here. And so that's good. Yeah, I would expect sodium EDTA to be more aggressive because the sodiums will break off more easily from the EDTA so that the EDTA can go and capture lead ions. Whereas the calcium would hinder it more. The calcium, because EDTA likes all metal cations, not just lead. It likes any metal cation. So if EDTA is wrapped around calcium, then that's okay, but it can also wrap around lead, and it prefers lead. So it'll be less aggressive because we have to exchange lead for calcium kind of thing. Does that make sense? So sodium EDTA is more aggressive than calcium EDTA. In fact, sodium EDTA is so aggressive that the only agent recommended for intravenous chelation therapy, chelation is this trapping. We're going to be talking about chelation in chapter 24. For children is calcium EDTA. That makes sense. You don't want to give children an aggressive drug, right? Well, are we out of time? 12:55? Okay, I'm going to stop here. So we'll just continue this next time.